Hello students. In this video we're going to learn about kinetic theory of gases. Kinetic theory of gases. Previously we learned about Dalton's law as well as Graham's law of diffusion. So if you want to learn those, just please go through the playlist. Yes, kinetic theory of gases people generally call about this one as KTG. The main aim of this topic is to discuss about to discuss about properties of matter, properties of especially gases uh, at at microscopic level. It means at very small level what is happening to the particles. So that we have to discuss. Means we all know the general properties of gases. What are the general properties of gases? They do not have definite shape, right? They do not have definite shape, but we don't know why they do not have definite shape, and that is going to be explained by this theory. And they are highly compressible, right? Gases are highly compressible, we all know that, and why, that we are going to learn here. And similarly we know that gases do not have definite volume, do not have a definite volume, so etc. So there are so many properties of gases. So gases travel very fast, that means the kinetic theory or the kinetic energy of gases is very high. Gases is very high. These all are the general properties of gases, and these properties, why these properties occur, what is happening at the microscopic level. So to explain those, the kinetic theory of gases is introduced. So first of all, theory topics are there, then later on derivation will also come, right? So first of all, let us see the postulates of kinetic theory of gases. What are the postulates of kinetic theory of gases? So if you take any gas in a container, this is a container, closed one, and there are large number of gas molecules. So the first point says all the molecules of gases, uh, all molecules of given gas are identical. Are identical. Identical means same in respect of what? With respect to their size, or you can say mass, or you can say density, etc. So if you take a container, so there will be large number of gas molecules, but all the gas molecules are identical in terms of size, shape, as well as density. So this is the point number 1 given by kinetic theory of gases. It is a very simple point. Second point, they said if you take this container, between these molecules there are no intermolecular forces. They said there are no force of attraction, or in fact negligible forces. That's why gas molecules can move freely in all directions. So that's the reason why they occupy the whole volume. If you put this gas in the big container, let us say this is a very big container, so if you transfer this gas into this container, it also occupy the whole space. Here we have written that gases do not have definite volume. Why they do not have definite volume? Because the intermolecular forces are negligible. So that's why whichever the container you take, whether you take big container or small container or any other container, so gases will fit into that one. So let us say the volume of this container is 1 liter, the volume of this container is a 2 liter. So if this gas is transferred into that container, the volume of gas becomes 2 liter. Means gas is that much amount only, but volume becomes increased. That's why we say the gases do not have definite volume. I will explain once again. You see the point first. Let us write the point, then I'll explain. They said there are no intermolecular force or negligible intermolecular force exist between gas molecules. Exist between gas molecules. So what happened? So due to that, because of this reason, gas molecules gas molecules take the whole volume which is available to them. Take the whole volume available to them. If you provide the 5-liter container, they will fit into the 5-liter. If you provide 1-liter container, they will fit into the 1-liter. So due to this point, we say gases do not have definite volume. This point will prove that why gases do not have definite volume. Got my point here? If there are intermolecular forces, they will hold them. They will pull it back, and that's why they will fix in the definite area. But here there are no fixed intermolecular force, that's why they will not have definite area. They will take the whole area which is available to them. Whole area, I'm talking about 2-dimensional, and in 3-dimensional you talk whole volume. If there are intermolecular forces, they will fix into the definite volume, but there are no intermolecular force. That's why gases are occupying the whole volume which is available to them. Understood? So I hope you got this point. Now point number 3, what they said is the total volume of gas molecules or the volume occupied by gas molecules is very, very less as compared to the volume of container, or you can say volume of gas. I will make small modification here. I can say the volume occupied by gas molecules. The volume occupied by gas molecules is negligible as compared to the volume of gas. What is the meaning of this point? Suppose you take a container, and let us say the container volume is 10 liter. Right. Now I kept X gas, let us say hydrogen gas. So hydrogen molecules will be there here. So they will also occupy some volume because they are standing at fixed position, means they will also occupy definite volume. Now the volume occupied by these molecules, is very, very less. Very, very less is, let us say, only 0.1 ml as compared to the, which is very less as compared to the total volume of gas, which means they mean to say there is large empty space. They mean to say there is a large empty space between gas molecules. Because of this empty space, the gases are highly compressible. We have studied in the beginning that gases are highly compressible. Why? That is what they are telling. Because if you take a container of 10 liter, right, in that you kept hydrogen gas. So gas molecules, the molecules are standing at specific position. They will also occupy some volume. The volume occupied by gas molecules, they said the volume occupied by gas molecules is just 0.1 ml, which is very, very less as compared to the volume of gas, that is 10 liters. So you can ignore this volume. So they mean to say volume of gas is nothing but volume of the container. So here volume occupied by gas molecules is ignored. Got my point here? 3 points. Once again, revision. So all the molecules of a given gas are identical with respect to the size. If you take a container, there are X number of gas molecules. All the molecules are similar in terms of size, mass, or density. So if you talk about one molecule, that will be similar or applicable to other molecule also, because all are identical. Second point says why they do not have definite volume. Why gases do not have definite volume? Because between gas molecules there are no intermolecular force, and that's why they are not bounded to definite volume. If the intermolecular forces are there, then they will fix it to the specified volume, but here there are no intermolecular force, that's why they can take any volume which is available to them. That's what they are telling. There are no intermolecular force existing between gas molecules. Of course, later on we will come to know this point needs some correction. That correction we will do afterwards. And similarly, volume occupied by gas molecules is very less as compared to the total volume of gas. As compared to the total volume of gas. Suppose you take a volume here, container 10 liter. It means the gas is 10 liter. But in that, the gas molecules, they are very small. So that's why they will occupy very less volume, which is 0.1 ml, which is negligible as compared to 10 liter. Understood? Yes. Now, point number 4. Point number 4 says gas molecules or the molecules of gas move in random direction. Random direction means they move in different directions and do not settle down. So they never settle down. That is what they say. So which means I can say like this: there is no force, there is no point of uh, gravitational force acting on molecules. So gravitational force is not acting, and that's why they do not settle down. They are not settling down means this says the gases do not have definite shape. So this point will prove or explain why gases do not have definite shape. When they will have definite shape, suppose example you take a container. So here gas molecules, if they settle down after some time, then they will attain definite shape. If they settle down, then they will attain definite shape. But here they are not settling down because there is no gravitational force acting on them. So there is no gravitational force, that's why they can move random directions, and that's why they do not have definite shape. Understood the point number 4? Now number 5. So when they are moving in random direction, they collide with each other. So molecules of gas as they are moving in random direction, so molecules of gas collide with each other, as well they collide with walls of container, right? So let us take this point here. So if you take a container here, let us put only one molecule. I'm not talking about large number of molecule. So let us take another molecule, two molecules. So they are moving in random direction, so they may collide with each other, or they may collide with the walls of container. So in this way the gas molecules strike with each other or strike with the walls of container. Now main point, you see, when they strike on the walls of container, they leave some force over area when they strike on the walls. So and that is called as pressure. Here during collisions also pressure will be created, but that pressure is very less as compared to the pressure created due to collisions with walls. I repeat once again. So during a collision with walls, uh, during collision with walls, with walls, they leave, gas molecules leave some force over walls of container, over walls of container, or that is also known as specified area. So this is called as pressure. So which means gases exert pressure. So why they are exerting pressure? Because they strike on the walls of container and then they leave some force over there. So force per unit area is called as pressure. So understood. Suppose if the number of collisions with the walls increases, suppose, then the force leaving on specified area increases, which means pressure also increases. So what I can say, the pressure of gas, the pressure of gas is mainly due to collisions with walls, collisions with walls. So if collisions are more with the walls, the pressure of the gas will be more. If collisions are less, the pressure of the gas will be less. Now next point, I hope you understood fifth point. So they collide with each other as well as collide with the walls, but when they collide with the walls, they leave some force, and the force acting over unit area is called as pressure. Now next point, very useful point. So gas molecules, all gas molecules move with different velocity, different velocity in different direction. So, okay, so means the velocity of gas molecules is different in different directions. I'll explain this point. This is a very useful point which is useful in derivation. Container you are taking here, you take two molecules, molecule number 1 and molecule number 2. The velocity of molecule number 1 and velocity of molecule number 2 are different. That is what they said. All gas molecules move with a different velocity in different direction, which means velocity of molecule number 1 is not equal to velocity of molecule number 2, not equal to velocity of molecule number 3. However, they move in different directions. Suppose you take X molecule, it moves in Y direction, it moves in X direction, it moves in Z direction. So the total velocity is equal to, so the velocity in all directions will be same. That is what they mean to say. Velocity of first molecule in X direction is equal to velocity of the same molecule in Y direction, which is equal to velocity of the same molecule in Z direction. Understood the point? Similarly, you take another molecule, second molecule also moves in y-axis, x-axis and z-axis. So here also the velocity of the second molecule in x direction is equal to the velocity of the second molecule in y direction, which is equal to the velocity of that same molecule in z direction, which means the velocity of the molecule remains same in all directions, but however the velocity of one molecule is different from the another. From here I will write one important point. So total velocity of the molecule v1x or v1x or vx1, I'll write vx1 is equal to square plus, yes, vx1 square. The total velocity I am finding vx1 square plus y1 square plus vz1 square is equal to, what can we write? Because all the directions it is the same, I can write 3vx1 square, which is equal to the total velocity of the first molecule v1 square. I repeat, this is a very key point. If you understand carefully, then the derivation will be very easy. I am talking about the first molecule. First molecule velocity is v1, but v1 is we have to add all directions, x direction velocity, y direction velocity and z direction velocity. So v1 x square, why I'm doing square? Because it is useful in the derivation, the coming derivation, that's why I'm taking square. So vx1 square plus vy1 square. So again, first molecule on y-axis, one molecule, one same molecule in z-axis, we are doing summation which is all equal, because you said vx1 is equal to vy1 is equal to vz1, so which I can write 3x1 square, which is equal to the total velocity v1 square. Got it? I repeat once again, I'll write once again here, listen carefully. I am writing that's only one molecule, this is the v1 molecule. V1 molecule velocity is same in all directions, that's why vx1 square plus vy1 square plus vz1 square, it is all equal. This is same molecule, I'm talking about v1, in all directions it is same, that's why I can write all are equal. So I can write 3v, you can say x1 square or x2 square or y square, which is equal to the total velocity of the molecule, that is v1 square, v1 square. So keep that in mind. Same thing you can apply for v2 also. Now you may ask me, sir, take another example, let us talk about v2. So v2 is moving in different directions, so it will have vx2 which is equal to vy2 which is equal to vz2. Now I'm doing square because this will be useful in the next derivation. So vx2 square plus vy2 square plus vz2 square is equal to what will come? All are equal, so I can say 3vx2 square, 3vx2 square, which is equal to the total velocity square, that is equal to v2 square. Right, got this point? So rewind the video, see 2 to 3 times. Okay, so I tried, maybe I must be going a little bit faster because video is becoming long, that's why, but see the video carefully and understand it. Now next point. Now the next point is about kinetic energy. See, kinetic energy of all molecules I have to think. So there are x number of molecules, I have to think about kinetic energy. Kinetic energy is equal to half mv square. As we said in the first point, mass of all molecules is the same. Mass of all molecules is same. But in the previous point we said velocity is different. All molecules move with a different velocity. So if velocity is different, so kinetic energy will also be different. So what can I say? The kinetic energy of all gas molecules is different. All gas molecules is different as they move with different velocity. So as they are moving with a different velocity, of course they have different kinetic energy. However, the velocity depends on temperature, so that I can say the kinetic energy of any molecule is directly proportional to temperature, because velocity depends on temperature. So obviously kinetic energy of any gas depends on temperature. Last point about kinetic theory of gases. You said they collide with each other as well as collide with the moles of the container. So the collisions among gas molecules, are, there's a very important word, it's asked in MCQs also, are perfectly elastic. So what is the meaning of word elastic collision? Let us take, suppose two molecules, this is a A molecule, this is a B molecule, coming with let us say kinetic energy 20 kilojoule, and this is coming with kinetic energy 100 kilojoule. So this is the situation before collision. This is the situation before collision. Now they collide with each other and after that they will move the direction. So again, A molecule and B molecule, there may be change in individual energy. So it may become 40 kilojoule and it will become 80 kilojoule, but the total energy will be remaining same. You see, 20 plus 100, it is a 120 kilojoule, and 40 plus 80. So here there may be change in the individual energy. You see, the energy of A molecule, this is before collision and this is after collision. So it is after collision. So the total energy is same. It's a 120 and 120. So total energy is same, but there may be change in the individual energies. That is what we say elastic collision. So it means energy of one molecule get transferred to another, but there will not be loss of energy. So it means there is no loss of energy. However, the energy may transfer from one molecule to another molecule. Now you may ask me, sir, how can you prove it? Suppose if the collisions are inelastic, suppose if the collisions are inelastic, then somewhere they will lose all energy and they must have settled down. They must have settled down means gases must have definite shape. If the collisions are inelastic, then gases must have definite shape, because if you are thinking that they are inelastic, they will lose the energy after some time. They will settle down. Means they will have definite shape. But we are not seeing that. Gases do not have definite shape, which means their energy is not losing or not gaining. So it means there is a conservation of energy during collision. So which means the total energy before collision will equal to the total energy after collision, but there may be difference in the energy of individual molecules. Right, this is all about postulates of kinetic theory of gas. Now let us derive the expression for kinetic theory of gases.
Subscribe now and press the bell icon. Never miss an update. Subscribe now and press the bell icon.